But before that, may I call Joel also to give maybe an opening or welcome remarks? Joel, this is Impronto. I ask, can you
All
please
right.
have the honor to have the welcome remarks? Okay.
Okay. All right. All right. Thank you, Elmer. And thanks to our three distinguished speakers this morning. And welcome to all of you to this special webinar on automation and related matters. So this topic to me personally is extremely exciting. And of course, this is of importance worldwide to everyone alive today. We're now in the fourth industrial revolution, and that's the convergence between the physical, the digital, and the biological. And certainly robotics and automation plays a key role, a core part in the fourth industrial revolution innovations and technologies. And so we're really happy that we have Elmer, who is a world-class expert, a preeminent expert globally in this area of automation and robotics, because this is really a really crucial foundation and building block for innovations that will be developed and are currently being developed now and will be developed further this century. So the impact of these technologies in our world today is simply transformative. So I'm very much looking forward to the talks of our three distinguished speakers today. Thank you.
Thank you very much, Joel. First of all, I'd like to welcome also everybody who are join us today. This is a very rare opportunity for us to listen to the talk of these three gentlemen, world experts on artificial intelligence, machine learning, robotics. So this is I waited this day because I'd been inviting them since 2 months ago to join on this, to become our keynote speaker. And I'm happy that we have lots of participants all over the world, and particularly here in the Philippines, mostly rather scattered from Mindanao, Visayas, and Luzon. We have participants, so this is a good opportunity for everybody to learn new technologies from our speakers that are important for pandemic situations. And of course, without further ado, I'm going to introduce to you our first keynote speaker, no other than Dr. Janjan Kabibihan, who received his PhD degree in bioengineering with specialization in biorobotics from the Scuola Superiore Santa Ana, Pisa, Italy in 2007. Concurrent with his PhD studies, he was accepted to the co-tutors PhD program of the École Normale Supérieure Paris-Saclay, that is in France. Therein, he spent 1 year with the Laboratoire de Mécanique et Technologie in 2005. He completed the Venture Creation and Finance programs at the University of Oxford in 2021, that is in the United Kingdom. And then from 2008 to 2013, he was an assistant professor at the Electrical and Computer Engineering Department, that is in National University, Singapore, which he served as the Deputy Director of the Social Robotics Laboratory. He is currently an Associate Professor at the Mechanical and Industrial Engineering Department of Qatar University. He is the lead and co-lead principal investigator of several projects under the National Priorities Research Program of Qatar National Research Fund. Dr. Janjan is an inventor with 18 patent families and has over 140 publications, both journal, books, and conference papers. He is an associate editor and also editorial board member of the IEEE Robotics and Automation Letters, the Frontiers in Bioengineering and Biotechnology, and also an International Journal of Advanced Robotic Systems, and Springer Nature Applied Sciences Journal. He was a co-founding assistant editor, an editor board member of the International Journal of the Social Robotics, and a co-founding organizers of the International Conference on Social Robotics. Ladies and gentlemen, it is my pleasure and I'm very proud to introduce to you our kababayan, Dr. Jan Kabibian. Jan, please.
Hello, everyone. Hello, everyone. It's really a pleasure to be invited over here. Passion and honor, especially si Prof. Dadios, ay former professor ko sa manufacturing and engineering management. So as you noticed in the in my background, I've been moving to different domains, different areas of research, areas of work, domains of work, in fact, and in different departments. I've worked in manufacturing, in bioengineering. I've worked in mechanical engineering, electrical and computer. So it's I have a special opportunity to work with top colleagues all over the world. And what I will present here in this presentation today will be somehow a synthesis or an integration of all those technologies. So let me share. And good thing it's really relevant, especially now that we are in the pandemic, and we look forward to post-pandemic recovery. What we've seen so far is that, excuse me, is my slide okay? Can you see my slide? Just a quick feedback.
Sorry, Jan, we cannot see it.
All right, let's see. Okay. Yes.
Yeah, fine now.
All right. So now, the
But
talk
Jan,
is about.
I hope you don't mind. We are going to record this.
Yes, of course.
Okay.
No problem at all. Now, yeah, so robotics, especially interactive robotics, service robotics, social robotics, as we've been waiting for an opportunity in these domains to get some, let's say, to get some attention. And when the pandemic started, oh, the robotics just came up, and the domains of social robotics and service robotics was a perfect fit for social distancing, um, for non-contact interactions. So I'll give you two examples of those domains that we have been working on even before pandemic, and now it's suddenly becoming mature. Okay, so this I have done a few days ago. I was supposed to give a different intro, but then when I looked at the service World Robotics Service reports by this International Federation of Robotics, one of the leading robotics associations, we look at this growth in sales from 2019 to 2023. These are during the pandemic and hopefully post-pandemic period. And as you can see, there is a cumulative annual growth rate increasing from 24% up to 32% every year. And this amount is not in the millions. These are in the billions of US dollars. In terms of unit sales, from 2019 to to 2023, we can see a jump from 173,000 units to 537,000 units. Going more specific, in more specifics, the robots in logistics are still growing. These are growth drivers even before, and they're continuing now. But as you can see, the growth rate of robots for public environments and defense is not so much. You can see the increase in robots, almost an exponential increase in robots for public environments. Logistics is linear increase, while we can see an almost exponential increase in robots for public environments. So in terms of areas, the top 4 to 7, the top applications are in inspection and maintenance, professional cleaning and disinfection, field robots, and um, exoskeletons. You see those that are having linear increase are there, but then we can see professional cleaning is in an exponential increase. So we look at the um, service robotics industry, and we see that every fifth service robot supplier is a startup company, and this is really exciting. And these they have just come up quite recently. So you can see that in out of the 889 service robot suppliers, there are 183 startups. Okay, so these are the trends. Again, these were I collected this. I screenshot everything September 2020. From this report, and as you can see, I highlight the areas that this IFR looks at as a trend, so as a technology trend. So they see construction machinery and robotics, telepresence robotics, and you can see the disinfection robotics out there. And at the accelerator part, you see business model as robot as a service. Now, all these three items that I've highlighted were reported in September 2020, and this was in parallel. This is confirmation of what we have been doing so far. And well, essentially, that's the outline of my presentation today. So construction robotics, disinfection robotics, and as well as business models, robots as a service. Now, first, all the projects that I will describe to you are funded by Qatar Foundation, and this is one of them. This is one of the national priority projects in Qatar. As you can see from here, and in social media, most likely, you can see lots of, turn off the sound. There are lots of videos right now talking about 3D printing, robotic 3D printing, construction, and so on. Yeah. So this is the first 3D printed construction house. What they normally do is they do modular fabrication in their shops, in their plant, and they take that to the workplace. Not in the workplace, but the land where the owners want to put them in. Okay, so that's one example. So also now, since we have some of the rovers now in Mars, they are talking about, obviously they have considered, even as a concept, they have considered building houses and structures in Mars. Now, what we're looking at is that growth in 3D printing construction market. So when we started in 2019, the growth rate was really negligible. It's at 4 million only. But as we are moving forward, we can see that growth growing to 14 billion US dollars. And what's interesting here is that you see the green one, the proportion of regions of high interest in this 3D printing technology is in Europe. Oh, sorry, it's in no, it's in the Middle East and Africa, as well as in Asia Pacific. Both of these regions are regions where we are in. Well, I am in, close or closely related to. So that's almost half of the market. Everything good so far in audio and video so far? Just a quick feedback.
Yeah, great.
Okay. Now we did this. Went through. Please check our website at www.qr3dprinting.com, where we have some of the latest technologies in 3D construction and 3D printing. So you can see we have evaluated all the technologies out there, and essentially there are robotic arms. Just to simplify, and due to time constraints, there are robotic arms and gantry type robots there. Now, we look at certain designs. These are samples of facade that can be found in Doha. These are train stations. You can see the beautifully designed facades over there. These are some of the buildings. You can see the facades there. What we want to do is to use 3D printing to create our own facade as well with various shape, non-standard shape, and with certain algorithms in it. So what we found was a honeycomb design, which can be structurally and aesthetically structurally sound first of all, and then aesthetically pleasing. So we compared FDM. This is a polymer-based 3D printing, and DMLS, which is essentially based on metal. We also looked at the algorithms that we have been using. So this is the Voronoi algorithm, and we want some non-standard shapes to use in our facade. So how does this Voronoi algorithm work? So there are cells that are created. First, you introduce seeds, okay, and the radii in the algorithm, and then the formation of the formation between 3 points will be uh, the intersection of that Voronoi cell. So first you introduce radii and then seed them as well, and then then you will get various shapes. So this is an example of our initial um, trials, let's say. So this is sunflower, and this is oh, we can also create various shapes. This is the emir of Qatar. We have algorithms now to create uh, interesting prints and design. So these are very basic. They're step one approach. Next one, we have parametric design based on Voronoi algorithms. And we want to use this as a Lego type, what they call this, honeycomb shape pieces that we will construct together. So that's the facade that we want. And the printing is like this. And it works on Voronoi algorithms. You can see what we want to do is that there will be non-standard shapes, various shapes that will be various appearances that will that the public can see. How does that work? So we have we of course we use various algorithms. Apart from Voronoi, we also use the traveling salesman ants, wherein this will optimize the movement of the 3D printer. Quite a lot of scripting involved using Python and Grasshopper. This is an example, and these are connected by magnets. So what we want to do, and this is the connectivity using magnets. What we want to do is that this is at our lobby at the College of Engineering. What we want to do is that to increase the interaction between um, live structures, real structures, we want our guests in the building to interact with these parts so that they can build and construct on their own and improve interaction. Now we move to subtractive manufacturing. So this is hot wire cutting. I'll just speed it up. So this is subtractive. As you know, as I've mentioned, my first love was manufacturing engineering, and now I'm going back. So that's the initial pass is hot wire cutting, and then milling procedure is done. Okay. So we have our own digital manufacturing. This in collaboration with University of Technology, Sydney. How does this work? So there are stations over here. There's this the robot station, and on the middle is the constructed wall or facade. In the middle, these are the parts that are being constructed. Okay, so I'll just zoom quickly. So because this is parametric design, whatever changes you make has an effect on all the rest of the parts. Okay, so there's a quick zoom. I make a change in the appearance of one of the um, polystyrene. Okay, one of the I want to change the part. Let's say I change one of the pieces there. I move one of the vertices, and the whole facade will change. So now life has become easier. We move from physical, what we know is physical construction before, the old style. Now we move to digital first. And then once we're satisfied, we complete the whole fabrication process digitally and then transfer that with, uh, with robotics, through robotics. So we do our in-house design of end effectors, with also this time with two collaborative robots. And we are creating here 10 minutes left. We are creating here a hexagon shape, and this is how that's shown physically. Okay. All right. So we do have our safety features involved. So what we're looking at in terms of the industry itself is that we develop our own end effectors. We design our own effectors, and hopefully we can sell to the industry. This is an hardware intensive activity endeavor, and we need mixers, we need robot arms. These are some of the equipment that we have in the lab now. And this is the new lab. It's coming in. We have set up. This is the new home of the robotic printing project that we have. Way forward, you know that I'm based in Qatar, and in in our neighborhood, in our neighboring countries, there are countries in conflict, and what we want to build for them is a refugee housing, modular refugee housing, and it looks like this. It's parametric as well, and this can be done with cement, with concrete rather, and a mix of concrete, glass, polymer, and so on. Okay, that's the initial design. So it's a big team. The team's more than this. So this is a team composed of architects, civil engineers, designers, mechanical engineers, and so on. I have 8 minutes left. Hopefully, you can extend that. We now go to the next government-funded priority project. This is in UV disinfection. There's a concept of telepresence control of a UV robot. These are my version of 3Ds of robotics, of COVID-19 in particular. Um, this virus is dispersed, it's dangerous, and it's dull. Okay, so WHO recommends cleaning. Well, this was the old recommendation, in fact. Um, uh, th- yeah, and so yeah, so just read through it because we're in a hurry. So what we know is that UV robot can kill pathogens up to 99.98% kill rate. And what we have is an autonomous robot as well as telepresence control for this one for safety reasons. Also, we are looking forward to, that's why the country is in a rush, Qatar is in a rush to provide solutions. We are looking forward to the World Cup in November next year. So we are really hurrying up to clean up public spaces for visitors. So this is what we have. This is the initial test that we have. This is autonomous control. And the next one is telepresence-based control. I'll just turn off the audio. So this is at my office. This is at the supposedly dangerous location. Okay, so that's just a quick test. Now, market segments that we're looking at is we're looking at global, regional, and local. In the regional and the local, we don't have much competition. And in the local scene, we are looking at the FIFA World Cup venues, the hotels, the business establishments. Primarily, the message that we impart to the guests is that the venue, we have done extra effort so that the public space has been sanitized for all of them. The market is big. From 2019, it was only that this is the disinfection service robots. It was 300 million only, and it's expected to reach 2.3 billion again by 2025. So these are the growth rate is from, as you've seen earlier, for service robotics, it was from millions of dollars, it jumps up to billions of dollars in market. Uh, yep. So we are trying to raise funds to provide service robots for at least 500, 600 units of service robots. Now we look at the business model. There's now a trend wherein there is what is called robots as a service, and you can think about this as Uber for robots, let's say. So that is when the user sends contacts the company through a service app, and then a service fleet is contacted. The service robot fleet goes to the company, and essentially the big advantage of this is that the company doesn't have to buy the robots because it's a fleet of robots that has to clean a public space. They don't have to buy it. The company owns the robot, but the users, the customers, will purchase the service of those robots. So it's a good investment. It's an easy entry for the company and as well as for the customers to take advantage of the. There, these are revenue models of service of startup companies. There are recurring fees, there are training fees, and also we can get some revenue from consumables. We have a founder team composed of course, engineers. It's a multidisciplinary team, and our advisors are among the top CTOs and technologists in the world. This is a recent exhibition in Russia at the St. Petersburg International Economic Forum. Let's have a quick look at the Qatar's pavilion. The good thing and good news and bad news. The bad news is we did not get any, not much referrals, not much contacts. The great news is not good news only. The great news is that the great news is that our very own Qatar Airways has asked us, has called us in, our team, to present use cases for robotics for the Hamad International Airport. So Qatar's airport is competing, is neck to neck in competition with Singapore's Changi Airport. They're competing in the top 5 airports in the world, and we want the management, the technology team of Qatar Airways and the airport wants to compete, wants to be on the top. So this is this is one of our proposals with a company called Being AI. So this is the next step of interaction. If you can give me 5 minutes, I'll give you more background. Is that okay, Dr. Dadios?
Yeah,
Professor
go ahead,
Dadios?
Jan. Don't worry. Go ahead.
Okay, so I'll give you a quick introduction of this technology. So what's the problem in robotics? Okay, what's the big problem that, as Professor Dodd just introduced me earlier, I have contributed to the international community of social robotics. What was the problem that we have found? You see, companies have died slow death in social robotics. Recently, we have seen Pepper dying. They're not supporting Pepper anymore. They're laying off workers. And we know the background. We know the reason why. Earlier, it was Jibo from MIT. and we have seen what do you call this? A few other companies dying slowly. The problem is interaction. There is a window of interaction. So the interaction with robots, the interaction for robots are good for the first 1 minute, 2 minutes, and after that, the interest slows down or disappears or dies along with the robots. So now, um, with what's needed there is the intelligence, okay, the machine intelligence to understand what the users want and what they want to hear. So in collaboration with Being AI, please check out that company. Um, I provided to them the A to Z instruction list for tourists coming into Qatar. So the company encoded what's the proper attire, what's the timing of Friday timings, what are the hospital contact numbers, what are the language currencies, and so on, time zones, and so on. So they placed this information into their engine, and the processing only took 30 seconds. There was no hard coding needed. There was no manual coding that's needed. And this is the output. Okay. So it's an interactive augmented reality system. Well, VR AR system. So this is my friend Amit from Being AI. So that's the introduction and so on. And this is the question and answer. No, that's not a good question. That's okay. So now, so here's one. So now the engine looks at the healthcare hospital over here, or somewhere here. Yes. So in context, the engine asks, the engine goes to the tries to understand the context of what is being asked and gives a specific answer. Uh, it did not read okay. It did not read all of the text over there, but it only answered in parts, just like a human being would do. Okay, so the engine provides an answer that is concise and that is specific to the question. So the benefits of this is it's context aware. The conversational AI understands the intent of the question. The AI finds symmetrically relevant info, then activates the speech module. And lastly, the best part, coming from somebody who has programmed robots before, training is 30 seconds only, and the AI responds in real time. There are no hand-coded inputs. To me, this is the best, really best, the best part, so that you can improve interaction between the visitor and the robot. So moving forward, this is some of the um, concepts that we're looking at. It's a check-in system and anything else that can guide passengers during their trip. Yep, that's it. Yeah, 3 minutes overshot. And thank you so much for your kind listening.
Wow, that was very impressive, Jan Jan. Congratulations.
Yeah,
Very good.
thanks so much. Thank you.
Uh, I'm sure many of our participants want to ask questions. So we have still 5 minutes for that. Anybody want to ask questions? Please. Yes, Joel.
Yes, John, thank you. That's
Yes.
a fascinating and excellent presentation. On the first part with the facade 3D printing that you
Yeah.
presented, I couldn't help but note that the geometry you came up with really is consonant with the artistic preference or design in the Middle East or Islamic
Yes,
design, which
that's
is
right.
great.
That's right.
But my question is, I know that these are not meant to be load-bearing structures when you combine together those elements.
Right.
But have you at all looked at the mechanical strength and durability of the material that you used? If you could comment on that.
Yes, we did. I did not include it for time. Yeah, we did some finite element analysis, a static one only, for that. But when we look at this in terms of walls this time, what's interesting here is that we what we want our next project to be is that some of the walls in the university will be constructed by these facades, and then becomes a problem now for some puzzle like toy problems. That's fine. Basic static analysis can do it, but then we are looking also into computational fluid dynamics models, wherein fluids we have to deal with the factors like the wind, like dust storms, and so on. We haven't done that, but what we have done is basic static analysis, load analysis only for our current application. We will do that. We will do a lot of that as we go along as we move forward in the construction of the houses. So that's in plan. That's happening within the next 1 year as we end the project.
Okay, thank you, and congratulations again on your excellent presentation.
You're very much welcome. I think the Nap sent a question on the being AI. If it's not, I maybe you did not hear the discussion, the audio. I can share that now. If can I ask a feedback if you did not hear that discussion?
The audio was not. We didn't listen. We didn't hear the audio of the video.
The audio. Okay, so that's the most important part, I guess, for for this kind of engine. I will play that again externally. Okay, I'm sending that to you now. Reducing the volume. I don't know how. Here. There you go. Okay. So in any interaction, there's welcome, and there's the information in the middle, and at the back there is the goodbyes. So what I was saying earlier was that there's context aware. The engine is context aware, and it does not say too much.
Maybe we cannot hear the audio, John.
Yeah. Can you try? Can you try again? Yes. Can you hear that now? Can you hear that now? Or still not?
No, sorry.
No. Oh. I don't know how else to fix this. Anyway, so just believe that it works, and hopefully we see that in the Hamad International Airport next time. It doesn't work. I don't know how. Why? Anyway, yeah.
Anyway, are there some more questions from the audience? You are free to ask now. And also, no better Jan. Oh, anybody from the audience, please speak.
Elmer, Giselle here.
Oh, wow, Giselle. By the way, Giselle is our current PAASE president. Okay. Yes, Giselle.
So welcome everyone. JJ, it's wonderful here to hear from you. And I just wanted to say that you should connect with Gobet Advincula and John Ryan, Kokoy,
we are. We are connected. We have a publication coming.
Yes, and they have all the discussion of the materials used for 3D printing and for construction of some structural or semi-structural parts.
Yeah.
So that was the subject of our webinar or fireside chat a few weeks ago. So thank you so much, JJ, for speaking. And I'd like to thank the other speakers today for joining us. Thank you, Elmer.
Very much welcome. Thank you so much. Thanks for this opportunity.
Yes, thank you very much, Giselle. Yeah, Jan, I have one question. It's really, I'm very much interested in your startup company.
Oh.
Yeah.
Mahirap maghanap ng pera. Funding.
Can you enlighten us more on how you progress, how you're able to make it as it is now? Maybe some background.
Okay. For that startup company, that was accidental. Maraming accidentals during this period. It was started. We never planned it. We never thought of it. Obviously, I wanted to have to venture off as I progress in my career. But this pandemic gave that that immediate stimulus, so that I can I can join part of the game, so to speak. And even looking at the post-pandemic, where it seems exciting in terms of the opportunities out there. So just a quick background. There was this funding grant raised by Qatar Foundation. It was a 3 months project. And what can we do in 3 months? Essentially, that's a question. What can we do in 3 months? And this is where the strength of networks come in, the strength of friendships come in. Yung mga pinaghihirapan natin for organizing conference, for conflict management with journals and conference organizations. This was where it came in. All of it came in. So easily, when the grant calls was raised, I just gave phone calls to my friends in China, in India, in France, in the US, in Singapore. So lahat yan pinagtatawagan ko, I sent emails to them, and please help me. How are you? These are the most important questions during pandemic. How are you? And can you help me? I have a problem. So these two are some of the relevant questions for in the community. And easily, yung isang kaibigan ko sa China said, "Oh, no problem. We have that robot. We're building that robot," and easily they helped us with the robot. Of course, on our side, my side is on the VR side and the telepresence side. So it's the strength of networking and strength of community that we have in the robotics community that helped us. The technology may or may not be as difficult as before, but what we need now are more expert advice and more consultation and advising in terms of um, the startup and how to start up a company. So technology, that's one part. We've been doing that for a long time, for 10 years, 15 years already. But many of us don't know the second aspect. And one of those critical aspect is finance, and then how to start up the company, how to form the team. And this is the reason why um, I enrolled in this University of Oxford program in entrepreneurship, and I completed it, and that gave me some confidence in jumping in jumping to that waterfall. Kailangan maging matapang, so it's a fearless jump. And the next problem, of course, is the funding and so on. So the ecosystem has to play a big part of it. Sometimes Singapore's ecosystem has been very good. Of course, US is there. Then we see other hotspots for excellent entrepreneurship ecosystems. That was not really easily available in Qatar, but then it's starting because of this pandemic. It has started to uh, kick off, and lots of funding is out there. Now on the side, I'd like to say hi to John Ryan Dizon. Hey, Kokoy. Hi.
Hello, sir. Gabibihan.
Hello there.
Good morning.
So, Professor Dadios, that's a quick
Okay.
introduction of how we started, and the accident and the opportunities that followed after.
Thank you very much, Jan. This is a very good opportunity for us to listen to your talk, and we learn a lot from there. And that I think that's a really important thing for us here in the Philippines on spinning up a company. As you mentioned, the connections is very important. This is what we lack here in the Philippines, I think. So once again, thank you very much, and keep in touch always. As always, thank you very much for giving us your time. I know you're very busy, so thank you.
Thank you so much.
Yes, is there other question? I think I heard somebody.
Yeah, this is Giselle again. I just wanted to recognize the presence of former President Fred Pascal of UP. So he's here, and he, rarely he really selects the webinars that he can attend. But at this point, I think he would be able to give advice on, business management and all that. So thanks, President Pascal, for joining us today.
Yes, sir. Maybe you can give us a pep talk also, sir. Just a quite, we can give you the time, sir. Please.
Well, he might be at several meetings, but he's certainly listening in. Yes, we will arrange that.
Thank you, Giselle. Yeah,
Yes.
that's something that probably we can talk about.
Yes. Thank you.
Congratulations, JJ.
Thank you so much, sir. Thank you so much.
And you're preparing yourself, by enrolling at an entrepreneurship course. I think that's a good initial step to familiarize our scientists and engineers with I call it intricacies, but it's not really that intricate, the intricacies of business.
Okay.
Thank you so much. Thank you. I look forward, I hope to meet you someday in person, and all of you, most of you. I'd like to know more later on. I'd like to know more if there are opportunities for Balik scientists, and I'd be happy to.
Absolutely. We're going on a campaign and, get our experts abroad to become Balik scientists funded by the DOST. Thank you, JJ.
You're very much welcome. Thank you so much.
Yes, with that, yes, JJ, we have many of our scientists abroad are coming for as a Balik scientist. So definitely, we like very much you to come back and learn, teach us more on these new technologies. So with that, again, everybody.
Sorry.
Yes, Rod. Yes, Rod.
Somebody is asking, raising a hand, sir. Gonzalo Sarafika.
Yes, Gonzalo, please go ahead. Al, please go ahead, Al. Al is a past president of the PAASE also. Al, please.
Sound is missing.
Hello, Al, we cannot hear you.
Can you hear me now?
Yes, Al, go ahead.
Perfect. I'll remove that headphone. Yeah, we've been training entrepreneurship for using the Innovation Core program of NSF in the US for the last 3 years in the Philippines. I'm a Balik scientist in 2015. Actually, I just met with 3 deputy of the Congress yesterday morning regarding the program, and they were asking us what's the next step. And clearly, you're one of the next steps, JJ, being able to come home with a startup experience as part of the Balik scientists in a special area of expertise like robotics is something that is very, for lack of a better word, sellable right now, the DOST. So contact me or Yusek Gev or Giselle. We can easily arrange. For me, the specific concern that attracted me in your presentation is the environmental utilization of robots, especially in very hazardous environments. I've encountered them early on. It's almost like a Roomba for cleaning pipes in very apoxic environment is one of the applications we've looked at early on, and very specific. But that's the kind of value proposition that I want you to look at, especially for utilization not only in Qatar or in the airports, but also in the Philippines. We have excellent scientists. We've try to look at special technologies, gigahertz detection for virus particulate, similar to breathalyzers that's being used in Holland and in Singapore now. Clearly, along those lines of elevated sensory capabilities with your robot will be a useful technology. So to me, there's a company that asked me to consult for, which I didn't take because it's a little bit difficult on the regulatory front. It's called Yuhu. They detect 6 different environmental parameters that are related to viral propagation and viability. And that's something that maybe you might want to consider. But good luck on your entrepreneur. I was an entrepreneur for 17 years in the US, raised over $40 million in venture financing. I can definitely help you out. But again, let's start first with your value proposition and your technology focus and your regulatory pathway to a product for market. And then maybe we can do that quickly and get you onto pitching very quickly to potential investors. Again, being in the Philippines, there's not a lot of VCs over here, but I still have my Rolodex of 100 VCs in the US and Europe. So maybe we can attract them. But again, I'm looking for any Filipino who's wanting to go take the path that I've taken before. So good luck and more power to you, and we'll stay in touch. I'll definitely work with Elmer on the connection with LaSalle. I've been a consultant for LaSalle for the last 7 years as well on tech transfer. So clearly, I'm happy to hear that you're trying to give back and try to connect back. Thank you.
Thank you so much.
There you are, JJ. Your
Thank you,
connections,
thank you.
your connections are right there.
Thanks so much. Thanks.
Well, there are question in the chat box. Mike Louis Enriquez has a question. Why print homes with concrete? What is the advantage?
This time we are using standard construction techniques right now. Of course, that's the basic one. We're still developing the technology. We're just starting up really in the technology, and just really fortunate that it happened at this time. We are looking also at indigenous materials, to that local materials in a certain location, and that's also part of the plan. And over our side in Qatar, I'm right now in Maldives. Over our side in Qatar, there are just too many recyclable tires that needs to be used. So tires is rubber from tires is one of the candidate materials that we're looking at, so that they can be put into good use. So it's not necessarily concrete that we're looking at, but it's just simply the initial. Of course, it has its structural properties, which is that's why we use it in construction. But apart from that, we're looking at other materials right now.
Okay, there's a last question from the chat box. Sir JJ, did you present your project in the yearly CES in the US? Thank you.
We plan to after the St. Petersburg Economic Forum gigs. We'll see how we can move forward in other big higher level demonstrations, and certainly our university can back us up in terms of publicizing this, especially now that we have our World Cup coming in.
Okay, since we have lack of time, maybe those who ask questions in the chat box, please check it, JJ, so that you can answer them. You can answer this with them personally. Okay,
right.
So let's move on to thank you
so
very
much.
much once again. So it's about time now to go to our next plenary speaker. I'd like to introduce to you. Oh, wait a minute. You can stop sharing now, JJ. So let us move on. We go to the next plenary speaker. This is very close to my lab also. in the person of Dr. Napoleon Reyes. He was born and raised here in the Philippines. He graduated in 1993 with a Bachelor of Science degree in Physics at the De La Salle University. As a young physicist who was keen to apply this knowledge in the industry, he immediately joined a small software development company called Vision 8 as a product design engineer. On a contractual project at Intel Philippines, he was exposed to the special needs of the industry and became more interested in programming. It wasn't long before he realized that he wanted to learn more about computer technologies and algorithms. So he came back to the De La Salle University to pursue master's degree in computer science. Then eventually a doctor of philosophy of computer science. While studying, an opportunity to serve as an assistant lecturer at the physics department of the LSU arose to him to help fund his studies also. So he applied for the job and finally realized and loved it more. Teaching full-time was never really part of the plan, but he discovered his passion for teaching and research and never left the academic world again. His involvement with the robot soccer research during his PhDs has spawned a lot of novel ideas and research papers. He now teaches at Massey University in Auckland, New Zealand. And in fact, he was nominated Lecturer of the Year in Massey University for quite some time, multiple back-to-back in 2018, 2017, 2015, 2014, 2009, and 2006. He was the plenary speaker of the World Symposium on Digital Intelligence for Systems Machines in Slovakia way back in 2018. And also in Hungary in 2011, International Workshop on Emotions and Smart Technologies in Hungary. My dear friends, ladies and gentlemen, it is my pleasure to present to you Dr. Napoleon Reyes. Nap, go ahead, please.
Thank you very much. Hopefully that everybody can see my slides. I just want to check.
Yes, it's okay now.
Okay. Okay. Thank you.
Before that, would you mind recording? I will record.
No problem. No problem, sir. Please go ahead. My presentation is focused on searching unknown terrains. And I have organized my presentation in such a way that I can introduce some basic terminologies and concepts so that the more advanced algorithms could be understood. I'm going to start off with the state-of-the-art D-Starlight algorithm. This is the core algorithm used by NASA's Mars rovers in outer space. I'm also very much interested in cleaning robots. And the algorithm I'm going to present today could also be extended to do this sort of task. Like, how do you make sure that the robot can clean each and every inch of an unknown terrain for any space? And in this talk, I'll be talking about how I improved this D-Starlight algorithm using a technique called Poisson reverse. Then I'm going to talk about how I combined fuzzy logic with D-Starlight with Poisson reverse to allow for both global path planning as well as low-level motor control. Then I'll talk about some results in discussion and show some simulations. First, I'd like to show some recent news about autonomous driving. Here's a sad picture of a fatal casualty. This involves a Tesla Model X, and it happened in 2018. This car was equipped with all the best technologies during that time. It's got 8 surround cameras, forward-facing radar, ultrasonic sensors. It can see 360 degrees around its neighborhood. It can see through heavy rain, fog, dust, and so on and so forth. However, as this photo shows, this this autonomous driving car is still not yet ready for today's requirements. So we need to develop more algorithms to address these problems. So even the best algorithms out there is not yet ready. Moving on, let's talk about unknown terrains. Imagine the problem of NASA. You want to deploy a Mars rover in space, and that will be in a very faraway planet. Mars is about 400 million kilometers from Earth. And in order to communicate with your Mars rover, it's going to take 26 minutes on the average just to send a signal. So teleoperation is not feasible. Your robot needs to operate in some autonomous mode. And for these rovers, they're given a mission on a daily basis. They'll be given some predetermined goals where they need to dig some rocks, get some samples, and try to find some evidences of the existence of life. So here's one example where navigational autonomy is vital. And the algorithm I'm going to present will be mostly suited to these sort of problems. And what about the current pandemic situation? We're currently living in this period of uncertainty and change due to this ever mutating COVID-19 virus. And it is only timely that we should keep on developing more advanced algorithms so that we can have self-driving cars that can transport goods and commodities between cities without human contact. And this is one way of trying to alleviate the spread of the virus. I would like to talk about some background on the algorithm I'm going to present. I would consider the mother of all optimal search algorithms is the algorithm called A*. This algorithm was developed at Stanford University by three scientists, Hart, Nilsson, and Raphael. And they provided an algorithm that guarantees returning the best solution every time a problem is given, provided that a solution exists. This is what we call heuristic and optimal search algorithm. 26 years later, it was extended to become dynamic A* by a scientist named Anthony Stantz from Carnegie Mellon. This dynamic A* is able to reuse past computations to speed up future computations. And this is what we call incremental search. And this is suitable for navigating unknown terrains. It was then further improved, made more efficient by a group from University of Southern California, headed by Sven Koenig. And that brought about the algorithm called D*Lite. Then, at some stage in around 2006, D*Lite was embedded into an algorithm called Field D*. This became the core of the algorithm used by NASA's Mars rovers. So for me, this was exciting because I'm fiddling with a well-tested and optimal search algorithm. And the challenge, of course, is how do you do better? It's almost impossible, to be honest. I'm going to show the results of my modifications, and I'll show some benefits from my algorithm. Field D* was well tested in the sense that these Mars rovers, Spirit and Opportunity, survived all the harsh weather conditions in Mars, and they were able to accomplish their missions. And that's through autonomous navigation. These rovers are now retired robots, and they've achieved all their missions. Let me talk about D*Lite. D*Lite makes use of techniques coming from artificial intelligence and algorithm theory. AI provides this technique called heuristic search. It is capable of goal-directed search. If you want to find a path from any source to a destination, this algorithm is going to reduce the work needed by making sure that only the relevant aspects of the problem will be considered for computations to try and reduce the amount of work needed to be done. Incremental search allows for the reuse of past computations to speed up future computations. This is quite interesting. So when you combine them together, you've got an optimal and incremental search. What I did in my research was to incorporate another algorithm called fuzzy logic. This is my favorite algorithm. I learned this from Professor Dadios. Fuzzy logic is an algorithm that mimics the way humans think. And this allows for the representation of vague linguistic terms mathematically. So you would like to quantify what you're describing only vaguely, and then you can come up with a precise problem-solving methodology. In my system, fuzzy logic is able to compute for the low-level motor control, and therefore I've got a global path planner as well as smooth control that can run in real time. So this is what I call fuzzy D-star light. The idea is very, very simple. D-star light computes for the waypoints, and using these waypoints, fuzzy logic will use them as a guide to smooth out the path towards the destination. The challenge here is that the world may be changing, and these changes in the world would require some course corrections. Therefore, the algorithm needs to perform replanning, and this needs to be done efficiently without wasting time. As can be seen in the diagram, a new path needs to be computed, and the idea is to make use of the past computations so that you don't need to start from scratch to solve future problems. So fuzzy D-star light with Poisson reverse is what I'm proposing. To get an idea of how navigating an unknown terrain looks like, what are the basic steps, let me introduce everybody to what NASA is doing. And this is what any robot would basically do. It involves a cycle of operations. And let us say that you're given a robot with an incomplete map. And this robot will use it as guide. However, this map is plagued with errors. So the robot needs to make use of its onboard sensors to verify the validity of the path. Given a predetermined goal and knowing a little bit about the world and being aware that there are some unknown obstacles that are not present in the map but could be encountered by that robot. And there are also some known obstacles. However, this map cannot be fully trusted. How will the robot deal with this situation? First, all the algorithms that I'll be talking about operate on graphs and trees. And so we have this, what we call 8 connected grid world representation. If your robot has got, let's say, 8 onboard sensors that can allow the robot to scan the environment 360 degrees, this is the simplest graph representation. 8 connected grid world as depicted by the diagram. There are some challenges involved. Firstly, the unknown obstacles may be actually blocked, but the robot thinks that they are traversable according to this incorrect map. So how do you deal with this? It's an error in the map. Another possibility is that there may be cell locations that are actually traversable, but according to the map, they are blocked. So the algorithm needs to perform course corrections and do the minimum amount of work needed to compensate for these for the ill effects of these unknown terrains. So here are the steps. The robot is equipped with some onboard sensors. It's going to sense the environment up to a limited range. For anything that the robot doesn't know about, it's going to optimistically assume that they are all traversable. This is what we call the free space assumption. The robot will compute for a path knowing that that path is not actually perfect. So it's going to go through this cycle of steps. It's going to sense the environment, calculate the path, and then move the robot one step towards the goal. As we can see here, it's going to see, for instance, some obstacles that weren't found in the map after sensing the environment. Then it's going to recalculate the path. That's why we call it replanning, to do this course correction, and then move the robot one step towards the goal. This is done repeatedly until eventually, hopefully, the robot ends in the target destination. The algorithm promises that if there's a solution to the problem, it will find one. Otherwise, if there's no solution, the algorithm will also be able to identify that there's no finite path to this predetermined goal. So challenges, how to do this very efficiently, how to make use of knowledge of the world, and as the robot progresses, learn more about the world, record those errors, those corrections in the map, and then compute for the exact steering and speed adjustments, translate them to wheel velocities, and then try to get to the goal. In the simulation I'm going to provide, I've got the following representations just so that everybody can understand what do they mean. I'm indicating my robot's position by a light green cell here. This is the robot with some incomplete map and with some errors too. And here we're going to consider some range of sensor range to identify the neighborhood of that robot. Then we also have this goal position, and then we have these dark colored cells indicating that they're blocked, non-traversable. The gray cells are traversable cells. And then for those unknown to be blocked cells, I'm marking them as peach-colored cells. So when I'm doing this simulation to compare one algorithm against the other, I've got many test cases, and I've got some metrics of performance that conforms to the standard way of doing things for navigation. Then I also have these cells that are unknown to be traversable cell. The robot thinks that they are blocked, but they're actually traversable. So let's have a look at some simple demonstrations first before I delve into more details. So I've got a program that will run in real time here. I'm going to get started off. I'll start off with some really simple ones before I show some more complicated ones. I just want to check, can everybody see this simulation?
We can see the presentation now.
Okay, I'm going to switch to my program. Stop share, and then I'm going to switch to another. Okay. Okay, hopefully everybody can see this.
Yes.
Okay, so here's a very simple representation of the problem in a grid world representation. The green object is my robot, the blue is the goal, and the peach-colored cells are unknown cells to be blocked. Initially, the robot will compute for the initial path. These green cells here indicate those cells that were examined by the robot. When you're developing an algorithm, you would like to minimize the amount of cell examinations so that you can speed up the computations. Then the robot will follow this shortest path computed. It's going to move one step at a time, just like what I mentioned, engaging its onboard sensors, checking for any discrepancies in the world according to the graph that it is using and according to the path it has found. Then, once it encounters those peach-colored cells here, the robot will find that, wait a minute, we've got some problem. We need to perform replanning. And in that case, that is where the robot engages another function to recompute the new path. And this needs to be done efficiently, and we want the shortest path. And for this very simple example, eventually the robot lands in the target. I'm going to show one more example just to some very important points. Let me see. Okay, here. The robot will also initially try to find the shortest path. Okay, sorry, I'm going to share another screen. The algorithm that I'm going to present are more efficient than the original D-Starlight when it comes to cases where the robot needs to backtrack and then perform a new path computation before eventually reaching the goal. In this example, I've got my green robot and it's going to follow this initial path. Let me just click. Moving one step after another until eventually he finds that there's a problem and then backtracks, recomputes a path, eventually finds a problem. So these backtracking maneuvers are those cases that I want to address. How to make it more efficient than the original D-Starlight. And this is the same algorithm used by NASA. Okay, I'm going to go back to my slides. I hope everybody can see the slides now.
Yeah, we're
Okay,
back.
yeah, okay. Now I'll talk about the details of this algorithm. This is the core algorithm. Each cell in the grid world will be represented by a set of variables. I'd like to mention, for instance, the keys here. The key will tell what is the priority of that cell when it comes to finding a path to the goal. And to make sense of this algorithm, I'm going to show some basic concepts too. Each cell is connected to another cell, and so based on their connections, we have some predetermined costs assigned to them. All diagonals will have square root of 1, and all horizontal and vertical connections will have a value of 1. Then just to drive some very important ideas, let's have a look at this case. Given that the robot is at the start position and looking at the graph where the robot has got 3 options to choose from on the way to the goal position, okay, which node shall the robot examine next to reach the goal? This is the idea behind heuristic search. Is it going to be node A, node B, or node C? What comes to the rescue is a heuristic guide. This is implemented using a heuristic function that is problem domain specific. The heuristic function will estimate the remaining distance of a state to the goal, and that will be used later on for this very simple formula called the F cost value. F cost is equal to G plus H. This is a very basic formula for optimal search. This is the main principle behind what I'm going to show next. So looking at the F cost, the algorithm can estimate from S to the goal via some node C, what is the total path length? It can be estimated by adding the actual path length, denoted by G, and then the estimate of the remaining distance to the goal returned by a heuristic function. This is just an estimate, so it's never exact, but interestingly, this will help bias the search towards the goal, and it's going to find the solution more quickly. So each cell will be evaluated using this F cost value. Now let me jump to this advanced algorithm, D-Starlight. D-Starlight, interestingly, performs the search from the goal position to the start node. It's in reverse order. This is done because by doing this approach, the heuristic now corresponds to the estimate of the start distance from a node C, while the distance from C to G is the estimate of the goal distance. If you add them together, that's the total path length. Now, this algorithm was made to take into account the changes in this dynamic world. We have two estimates for the goal distance because the algorithm needs to be able to identify, okay, the world is changing. Is it for the better? Is it for worse? And we've got a sequence of steps and formulas to make it, to allow it to find the shortest path. So G and RHS, those two values will be examined by the algorithm to determine which cells will be relevant in the computation of a shortest path. So the basic idea is that if a cell in this grid world is locally inconsistent, that means if its G value is not equal to its RHS value, then place that cell into a priority queue. That means it needs more computations. And that is relevant to the problem that we're dealing with. And this is the complete pseudocode of this DSR-like algorithm. We can look at it in a bird's eye view first. We've got here routine 1 and routine 2. These set of routines will compute for first the initial planning, the initial path to the goal, and number 2, these statements here will cover the robot traversal and replanning if necessary. It's going to detect if the world is changing and if there are any discrepancies in the graph as compared to what is observed in the real world, then some updates will be done. And that's where the beauty of the algorithm happens. Let's have a look at some basic steps. We've got here the initial planning. So let's consider this very simple grid world. We've got the robot here, and we've got the goal position here. Find a path from S to G. Of course, in the real world, the problem will involve millions of cells. But just to understand the algorithm, this is how I analyze the algorithm in the first place. First, the algorithm will assign values to each and every cell. We've got G and RHS, the estimate of the goal distance. All of them will be set to infinity. That means the robot doesn't know anything about the world, and it will soon find out how to get to the goal in an efficient way. The algorithm starts off by looking at the goal position as marked by G. RHS here corresponds to the estimate of the goal distance. The distance of the goal from itself is 0. So that's the only thing that we know for sure. So the algorithm starts off by placing this goal node into the queue. This is the list of nodes that needs to be computed. Then from there, the algorithm is going to expand this vertex here. It's going to examine all the neighbors of this goal, and then they will be updated according to their G and RHS values. So this algorithm will propagate information to the neighborhood of cells, and that will be done repetitively. We've got a while loop here. The algorithm is going to consider those locally inconsistent cells. Then from these locally inconsistent cells residing in the queue, it's going to pick the next cell that is more relevant to the problem based on the key values. These key values corresponds to the F cost that we saw earlier. The smaller the F cost, the more relevant that cell is in solving the problem. And that will be done continuously. For this example, it's going to take about 5 steps before the algorithm finds a path to the goal. And from what we can see here, even without looking at the formula, what we can see here is that the G values will help the algorithm identify the shortest path to the goal. By greedily picking the next value of G from a neighborhood of cells, from 3 we will find that 2 will be the next smallest, and then from 2 the next smaller value is 1, and then eventually 0. The algorithm is able to work out the shortest path. And interestingly, this algorithm guarantees that it will always return a perfect solution to any problem. Now, this is my contribution. D-star light with Poisson reverse. What I have observed after studying this algorithm is that the algorithm is not able to remove circular dependencies. Let me talk about it using an example. When the algorithm detects that some areas in the world has changed, let's say maybe a cell is discovered to be blocked, and the algorithm needs to compute for the new path. A neighborhood of cells needs to be examined, and the algorithm does not need to start the computations from scratch. If let's say here, let's say my robot is positioned at node U, and then using its onboard sensors learns that this cell here is actually a blocked cell. So that means there's some errors in the map. Or maybe the world has really changed. Perhaps this region here became too soft for navigation. It's a hazard, for instance. Then the algorithm is going to look at the neighborhood of cells, and it's going to find a new segment that will be used for this path computations. It's going to examine a neighborhood, and it's going to look at these neighboring cells based on their G value and the C value. The C value corresponds to the direct link costs. How far is one node to another? While the G value is the estimate of the distance to the goal. The algorithm will pick the one with the smallest G value plus C value. So here, for instance, 3 plus 1.4 is 4.4, 5 plus 1 is 6, and so on and so forth. If you pick the smallest one, eventually, for this particular example, we will find that A is the minimum neighbor of U. And as the name implies, I'm going to poison some links that are not very, that are containing some incorrect values. If U finds that A is the minimum neighbor, it's going to set U to have this property that the parent of U is equal to A. Now, in my technique, I'm going to check, what about A? What is the parent of A? If the parent of A is, parent of A is U, then we have a loop. And if there's a loop, that means it's actually a useless information. So I poison it by setting some variables to infinity. Those estimates of the goal distance for those cells within a circular loop becomes poisoned. So this poisoning will have to be done in 2 levels. Node A, after the poisoning, is going to check to see what are the neighbors of A, and for those neighbors that are dependent on A in their computations, they will be poisoned too. And we will see the results later on according to some experiments. Lastly, I've got this fuzzy logic algorithm that will smooth out the path to the target. The cascades of fuzzy systems will compute for the exact steering angle and speed adjustments that will be translated to the left wheel and right wheel velocities, for instance. I've got another paper for this fuzzy D-star light, and I've got a pseudocode depicted in this diagram here. What happens is that the next waypoint is calculated using D-star light because it is an optimal search algorithm. From that next waypoint, I can now calculate the angle from that waypoint as well as the distance from that waypoint. And then I can compute for the steering angle, speed adjustment, and then translate that to the left and right wheel velocities. And the algorithm will proceed by engaging D-star light again, check for any changes in the grid world, then pass the waypoint back to the fuzzy logic, and then the process repeats. I've got some more interesting examples later on so that we can see how this algorithm is able to handle a confounding grid world where the algorithm will have to perform many replanning tasks in order to reach the goal. I'm going to show this later on, but just to generalize what is the overall observations. So I have pitted D-Starlight. This is the algorithm used by NASA versus D-Starlight with Poisson reverse. This is my proposed algorithm. And I have checked how much work is D-Starlight doing versus the algorithm that I've proposed. And I'm looking at the reduction in the state expansions. The number of state expansions in this grid world is largely attributed to the running time costs of the algorithm. Then, based on those improvements in terms of the reduction in state expansions, I wanted to see why is my algorithm doing well and in which particular scenarios. So I'm also keeping track of several performance metrics. I'm looking at the number of backtracking maneuvers. If the robot needs to backtrack, I'm keeping track of them. And I've examined many grid worlds with different topologies, different complexities. I'm looking at the number of looping dependencies, those circular dependencies, the number of obstacles encountered by the algorithm on the way to the target, the number of vertex expansions, replanning stages. Then eventually I was able to generalize that this proposed algorithm brings about some benefits in terms of efficiency in calculations. That is in terms of the reduction in the number of state expansions based on a combination of parameters. When the number of looping dependencies increase, the number of obstacles encountered by the robot increases, as well as the number of backtracking maneuvers increases. I have found that actually this D-Starlight with Poisson reverse is giving us some benefits. But the benefits is not like 50%. It can go 6% or less, depending on the combination of these parameters. I would like to show some more simulations before I end this talk. I'm going to switch to another screen. I'm going to share this screen just a second. Okay, I'm going to reset the program. Hopefully everybody can see the simulation. Just want to confirm.
Yeah, you can see it.
Okay, thank you. I'm going to press reset so my program can keep on resetting. So this is the algorithm in computing live as I speak. The green is the position of the robot, and these peach-colored cells are actually unknown obstacles. So the robot thinks that they are traversable according to an incorrect map, but the algorithm using the sensors eventually finds that, wait a minute, they're not traversable. So the algorithm keeps on backtracking and looking for a path to this goal position here. And the colors that I'm rendering here indicates the amount of work done until eventually, as we can see, the algorithm is able to move the robot towards a target. Okay, I'm going to switch back to my slides. So what I've presented here is actually a combination of 3 papers. And I know that more work needs to be done. What I find interesting is that the same algorithms could be combined with another algorithm called a greedy mapping technique. And in my opinion, it will help sweep the floor for cleaning purposes. So this is also one of my interests. Cleaning robots definitely is what I wanted to try in the future. As a computer scientist, because I'm not a hardware person, I work on simulations, but they can be actually implemented in a real robot. Just maybe to show everybody what I did with a real robot previously, I wanted to share just one more video. The fuzzy logic techniques that I've worked on before actually work on the real world. So we've got some very simple robots because I was trained by Professor Daniels to work on robot soccer. So eventually I came up with a simple robot soccer system here, but without any help from the students, it is just very difficult. I'm going to share one last screen before I end my talk. Just a second. Couldn't find the video. I'm just wondering, can everybody see some video?
Yeah, we can see it now.
The robot soccer?
Yes, yes, that's fine.
Okay, so this is just the pure fuzzy logic, and I was calibrating this at our laboratory here. As I mentioned, I'm not a hardware person, so we had to buy these robots, and then I worked on the software. So we can see that it can do this navigation thing that we needed. But this is just a pure fuzzy. I did the fuzzy D-Star Lite just recently, and I didn't have the chance to do it in a real robot anymore. But I would be very keen to collaborate with anybody who would be interested in the future. I think that ends my presentation. Thank you very much.
Okay. Yes, thank you very much, Nap, for that novel algorithm that you make. Now the floor is open for question and answer. Yes, Al, are you raising your hands?
I was about to, but yes, thanks for the very enlightening fuzzy logic debriefing again. Had this about probably 10, 12 years ago, and I practically have forgotten how advanced mathematics gets incorporated in the whole Mars rover. We developed it at Rensselaer early on in the 2000s that I saw it in action. But my question is mainly for helping the group in LaSalle, because you know that Elmer and Raymond and the group has been very active in PGraph and various types of mathematical modeling. And Raymond has been always asking about how we can up our game by actually developing our own algorithms. And to me, this is a direct appeal to you in the sense that we can probably at least look at real live problems in the Philippines, and thereby using your expertise in the back burner, if you want to call it, to help us get better models in terms of, I know they've been doing predictive for vaccine distribution over here. And I don't know if Elmer was involved with that, but I know Kay, and who's past president of PAASE as well, and Raymond, who's both PAASE presidents, are active in that aspect. How do you think your capability at this point, coming now that everything is Zoom, is that possible for you to do, Nap?
Oh yeah, maybe we can talk about first. We can narrow down what sort of problem we would like to solve. As I mentioned, I'm working on simulations because I'm working almost alone.
I mean, that's exactly, we have pieces of the puzzle. That's how I also interpret technology commercialization and utilization. All of us here in the audience, 100 of us, have pieces of the puzzle, and being able to compare what do you have and what can we share, what we work together makes our work even more not only utilized, but actually ups our game altogether.
For instance, this cleaning robots, I'm actually interested in that, but we need the hardware. For instance, I can work on the simulation. We need the hardware. We have a global path planner and low-level motor control, but the actual actuators, the design of the hardware.
We have that in Lasal. Elmer has all the actuators, and Nilo Bogtay has medical devices for, we've been developing medical devices for the last 6 years, almost funding of 100 million. I can see the predicted capability. If we can do the programs, indeed, that's something we can collaborate on. So I think we'll probably tap you on that one, Elmer, huh? Do this with NAP, okay?
However I could help, just let me know.
That's perfect. Thank you for agreeing. So we will get back to you. I'll talk to Raymond after this if it's not in the audience. But definitely Elmer has already 2 or 3 proposals in mind.
Okay. That would be great. Thank you.
Okay, thank you very much, Al. Any more question? Yes, Nap. I have a suggestions for you. Your algorithm is very good. It is new. It's very efficient. Would it be possible to use that algorithm for contact tracing?
Contact tracing.
We have problems here in the Philippines identifying people. Where are the locations of them? Whether for every affected individuals there are obstacles. Who are the contacts? So I think the idea of this algorithm can be implemented, or what can you say?
As it stands, the algorithm was designed for pursuing the infected person. If you want to pursue the infected person, the algorithm will pursue it, even if that person goes to an unknown terrain. So it is now ready for that. But for contact tracing, that will require some triangular, some sort of triangulation. In my opinion, that's another problem. But of course, it is also part of search. But at the moment, I couldn't think of any algorithm directly from the top of my head that I could recommend. But at the moment, for pursuing optimally anybody in any unknown terrain, regardless of the world is changing, immediately it is ready.
Okay, thank you very much, Nap. Anybody wants to ask question to Nap?
Yeah, just to follow on your question, Elmer, on the contact tracing, we've been trying to get, I'm part of the ASEAN Medical Device Hub, and I'm always wanting to transmit technologies between Singapore and the Philippines. And one of the devices they develop for contact tracing is like a necklace or a beeper that will turn red if you're within a contact trace or a positive person. So you initially, if you're negative, you're green. But as you walk around Green Hills and you bump into someone that's negative, it will beep, alert you. That's the level of technology. And that's how I was trying to, when I was watching you do your path tracing on the goal, that's exactly what I had in mind on contact tracing, but it's not as concrete yet on how do we go about that. But more indeed of tracing the, but I agree with you. Right now, we're hunting for variant D infected. And the more that we can plot them out as alerts, may be able to also assist the contact tracers to make sure that the exposure around those environments might be less, or maybe directing them away from where the variant D infections are happening. So that's just throwing it out there. But clearly, it's easier said than done. but it's a good exercise in terms of how do you use fuzzy logic delight need to be able to assist our hunting for variant B infected patients. In that, we only have 36 right now, but I'm sure there's more out there. But if you tell me don't go to Green Hills, then I'll not go to Green Hills. I live there, but I'm not going out of my house. Thank you.
Definitely, there's some interesting opportunities there. Thank you for mentioning that problem. I will start thinking about it because definitely these algorithms needs to be tweaked again to address those problems. And if we can estimate the exposure of people and quantify the likelihood that they got infected and therefore needs to be traced, that would be interesting, because if maybe we can predict who are those people who are not in direct contact but maybe got infected without them knowing about it, that would be interesting.
Yep,
That's
exactly
an interesting algorithm.
Yeah, that would be something that you might start noodling about, because variant D has about 8 times more capable of infecting people around you. That's why India and Indonesia are suffering big time right now. So we don't want that in the Philippines. And you can do anything about it with Elmer. Good luck. Any help from my side, I'll help you guys.
Thank you very much. I really appreciate it.
Thank you.
Yes, Al. Yes, that's a very good problem to solve. Nap, you have already the technique, and I'm sure it's easy for us to collaborate on that. So, yes.
Perfect. Thank you. Let's talk about that offline and let the next speaker go. Thank you.
Okay. In the interest of time, we can go to the next presenter. Once again, thank you very much, Nap. But before that, allow me to acknowledge my co-chair of the PAASE Rec 10, Pros Nabal. Pros, how are you? You can say something and welcome our participants. Hi, Pros. We cannot hear you're muted, Pros. Unmute ka. Your microphone is off. Sorry. Pros. I cannot hear Pros, so maybe we can proceed. So once again, thank you very much, Nap. It's about time to go for our last keynote speaker. Let me introduce him. In the person of Dr. Rodrigo Hamisola. Rod is a graduate from Mechanical Engineering, Bachelor of Science in Mechanical Engineering at University of the Philippines, Diliman. That was in 1993. And he got his Master's of Engineering degree in Mechanical Engineering from the National University of Singapore in 2001. And also a Master of Science degree in Electrical and Computing Engineering from Colorado State University in 2006. And of course, a PhD degree in Electronics and Communication Engineering from De La Salle University, Manila in 2009. He joined De La Salle University as Assistant Professor in 2008 and went to Toyota Motor Philippines as R&D Manager in 2011. He was a postdoctoral research fellow also at Daegu Gungbok Institute of Science and Technology in South Korea, and later was a senior research fellow in Istituto Italiano di Tecnologia, or IIT, in Genova, Italy. He is currently an associate professor of in Botswana International University of Science and Technology in Palapye, Botswana. His research interests include control of cooperative drones and robots, machine learning in motor imagery and addiction, and exoskeleton augmentation and rehabilitation. My dear friends, ladies and gentlemen, I'm very proud to present to you Dr. Rodrigo Hamisola Jr. Rod?
Yes, sir. Thank you very much for that very kind introduction. And I need to share my screen.
Yes, you can share it now, Rod.
Nap is still sharing. Or can I just share mine?
Yeah,
Okay,
you just share it.
Okay, there you go. Okay, so that's my screen now, and F5.
Rod,
Okay,
would you mind
so-
if we are going to record your presentation?
Not at all, sir. Go ahead. Yeah, thank you.